Welcome to today's chemistry class. For today, I will help you with chemical kinetics. I want you to pay extra attention as this part of chemistry is very much important because most of the questions in your exam come from this same topic. So I just want you to pay extra attention. Before I start, just ensure that you subscribe to this YouTube channel and follow our Facebook page so that you will be updated or notified whenever a new video is posted. For now, let's start. So now, what do you understand by chemical kinetics, or what is chemical kinetics? Note that chemical kinetics is the study of the rate at which a chemical process occurs. I repeat, chemical kinetics is the study of the rate at which a chemical process occurs. I've marked this. Why? Because a rate, what do you understand by a rate? So a rate is just how fast a chemical reaction occurs. So chemical kinetics will just be studying about how fast a chemical reaction occurs. Apart from that, besides information about the speed, which is the rate at which reactions occur, kinetics also sheds light on the reaction mechanism. What do you understand by reaction mechanism? Exactly how the reaction occurs. So apart from the speed of the chemical reaction, chemical kinetics will help you understand how that chemical reaction occurs. So now, before I proceed to the other part, are you guys clear on the introduction on this part, or what you're supposed to know about the chemical kinetics? Hello? Okay, so I assume you guys are clear, though you're not saying anything. So now, when you just see the word lead, what should come into your mind? Lead. When you see the word lead, what should come into your mind? So now, when you see lead, it's a concentration. You get? It's concentration of what? Concentration of either, let me write nicely. So when you see the lead, I don't know why this is so doesn't okay. So when you see lead, when you see lead, what should come into your mind when you see lead? You need to know that lead is a change in the concentration over the time. You get? Per unit time. So this deals with what? Concentration. Concentration of either the reactants or the products. You get? Concentration of either the reactants or the products over what? Time, per unit time. So I want you to mark this. This is what you're supposed to know here. So I say, when you hear the word lead, know that it's concentration over time. That concentration is the concentration of the reactant or the product. Now, what can be the units of this lead? What can be the units of this lead? Hello? Hello, I can't get you. I'm too fast. Okay, I repeat. Okay, let me repeat. Okay, so on the introduction, are you guys clear? Or now I explained, are you clear before? Hello? Let's do it first. Are you clear on the introduction, or I just talk about the lead? Do you know now? Yes, you're clear now. Yes, thank you. So now let's focus on a lead. Now, what do you understand by a lead? As I said, a lead is how fast a chemical reaction occurs. Now, this same lead is just a change in the concentration of the reactant or products per unit time. Rate itself is a change in the concentration of the reactant or products over time or per unit time. Because here we're trying to study chemical reactions. And for a reaction to be there, are reactants. You get? You can't have a product minus a reactant. So this rate now here is the is change in concentration of either the reactant or the product over time. You get? So this is what I was trying to illustrate here. Say rate. I just want you to master this because this is what you're going to be focusing on. So rate, as I said, is change in concentration. You get? Change in concentration of what? This concentration can be the concentration of products or reactants. You get? Over time. You get? Over time. You get? So for chemists, the chemists, they must initiate a chemical reaction first in order to study chemical kinetics. You get? So a chemical reaction is initiated. As the chemical reaction is initiated, what's happening in the reaction? There will be reactants, you get? There will be concentrations of the reactants, and time will be measured. So therefore, a rate is a change in the concentration of the reactants or products per unit time. Is it clear on this part, or do I need to explain more, or how is it? Hello? Clear? Thank you. So now, this is what I want you to remember. Once you just see rate, remember concentration over time is a change in the concentration of the reactants or products per unit time. Now, let's focus on the units for this. We need to come up with the units for this. So concentration itself, if you remember more concept, concentration is equal to what? Number of moles over volume. This, you know, the number of moles, that's measured in what? Moles, not so, moles. And then over, what's volume? Volume is what? In liters, not so. So therefore, concentration itself, it will be represented by what? Mole per means over per liter, not so. Yes. So now here, and then mole per liter can also be written as what? Molarity, just capital letter M. So the vice versa, either way, it's okay. If you want, you can just write this capital letter M representing molarity, which is mole per liter. Or if you want, you can just write this mole per liter. It's one and the same thing. So concentration in mole per liter can be represented by what? Molarity. So now, here on your top part, we have mole per liter. I just want you to come up with the units over. Have you seen down here? Time is measured in what? Seconds. Time is measured in what? Seconds. Now, what do we do? Laws of indices. When we take this thing up, we want to make it to be on the same base. So the units will be mole, you get? Mole per, have you seen this over? It can also be written as -1. This one, we take it up, that's it. It's like that. Why is it like that? Because laws of indices, if you remember, negative a raised to the power negative can also be written as what? It can also be written as 1 over a. You get? This can be written like that. That can be written like that. So when we take the liter up, it's going to adopt the negative. When we take this seconds up, it's going to adopt the negative. So therefore, these are the units for this rate. You get? So these are the units. Is it clear on the units? The units that we'll be using? Yes. So now, from here, we know that mole per liter, that's molarity. It can also be represented by M. Therefore, this can also be written as capital letter M, molarity, per seconds, like that. Just see, here on top, you present it with capital letter M because that's molarity over the seconds, you get? So this is just one and the same thing. So if you want, in some books, they like just using this one direct. If you want, you can use this as a unit. You pick any. So I don't know which one we'll be using. You'll be telling me the units that we'll be using. So once you see the rate, concentration over time should come into your mind. The units, mole per liter per second, or it can be molarity per second. Should I proceed on the other part? Are you guys clear? How many are clear on this part? On the units and the late? Hello? I want to hear from others. Are you guys okay? Or should I repeat? Is it making sense or not? I want you to. Hello? Are you guys okay? I can proceed? Thank you so much. So I want you to remember, once I talk about the late, the unit, I'm sure you should take a screenshot, and you have in books, you should be telling me this because we'll be using this. Thank you. So now let's proceed to the other part now. Yes, let's look at factors that affect reaction rates. Factors that affect reaction rates. I'm from talking about a rate, which is how fast a chemical reaction occurs. Now, there are some factors that affect reaction rates, which can make a reaction to be either slow or fast. You get? So now, the first one, we have physical state of what? Reactants. The same reactants you're trying to react. You get? They are in different phases. Is it a solid, is it a gas, or is it a what? A liquid. So the same reactants can have an effect on the reaction rate. You get? The reactants can make the reaction to be fast or to be slow. You get? So the physical state of the reactants. Is it a gas? Is it a liquid? Is it a what? A solid. So now, let's look at this part now so that you understand. So homogeneous reactions are often what? Faster. What do you understand by the word homogeneous? What do you understand by the word homogeneous? Homo means same. Homo means same. So homogeneous reactions, such as reactants in the same phase. Reactants in the same phase, such as you're using solid solid, or is it liquid liquid, or is it gas gas, are often what? Faster. Yes. So if you're reacting, even in just real life, practically, when you are reacting even liquids, that reaction can be what? Fast. So we are simply saying homogeneous reactions are often what? Faster. Now let's look at the other one now. Heterogeneous reactions. Hetero means what? Different, which means now the phases are different. So here you're having a gas with a solid. You get? It can also be maybe a gas with a liquid. You get? Are faster if the surface area is what? Increased. Now, for heterogeneous, there is a condition. You get? So these reactions, what can make these heterogeneous reactions to be fast? It's when the surface area is what? Increased or modified. You need to do something on the surface area. You need to change the surface area. Failure to that, the reaction will be slow. You get? So for homogeneous reactions, they are very fast. But for heterogeneous reactions, there is a condition to make it faster. You need to ensure that you modify the surface area. For example, fine powder reacts faster than a pellet or tablet. Yes, fine powders can react faster than a pellet or tablet. A tablet is big, a pellet is big, but fine tablets can react faster. For example, even just a Panadol, like Panadol, you're trying to give a baby. Can you give a baby a big tablet? No. Why do they try to crush to make it into fine powders? It's because it can be easily absorbed. For those who study medicine, farmers, you relate with this. So the moment you're having fine powders, the reaction will be faster. But big pellets or whatever tablets, big tablets, the reaction will be what? Slow. Is it clear before I proceed to the other part on this part? Oh, I'm too fast. Sorry. Where should I start from? Like on the physical state? Homogeneous. Okay. Yeah, you should be telling me so. I just want you to be hearing from you. Thank you so much. So like I said, yes, on the homogeneous one now. So homogeneous reactions, we have homogeneous reactions. So just by the word homo means same. Homo means same. So these are reactions whereby you are having same reactants. Same reactants. You get? Homogeneous reactions. reactants are in the same phase. Example, you can have maybe reacting just solid, or you can be reacting liquid, or you can be reacting gas and a gas. You get? And this type of reaction, homogeneous ones, since because they are in the same phase, these reactions tend to be faster. These reactions tend to be faster. They are fast. As a result, that's an effect it has on the reaction rate. So it makes the reaction rate to be fast. So homogeneous reactions make the reaction rate to be what? Fast. Are you clear, madam? Thank you. So now let's quickly look on the other one. Now, this one is heterogeneous. Hetero means different. Hetero means different. So here whereby you're having different reactions. You're having different reactions. Not so, like different reactants, in short. Here we're having different reactants. For example, you can be reacting a gas with a what? A solid. These are the reactants. These are different. So here they are saying that heterogeneous reactions are faster if the surface area is what? Increased. Have you seen? Now, for heterogeneous, there is a condition. There is a condition. For them to be fast, for this type of reactions to be fast, there must be a modification. They must modify the surface area of either the solid. The solid must be modified. And maybe it must be crushed into fine powders to reduce its surface area. It becomes small so that it can be fast. Further to that, these reactions will be slow. You get? So heterogeneous reactions are faster if the surface area is what? Increased. Example, fine powder reacts faster than a pellet or a tablet. So here that's where I was trying to explain that even can you give Panadol to a big tablet, if to a baby? No, they like crushing that. Why do they crush that? Because that they know that the bigger the tablet, in terms of when the baby swallows it or it goes inside the GIT, it won't be absorbed that much because it's big. You get? But when it's crushed into small particles, it can also be easily absorbed. I just want to talk about those who want to do medicine. You get? You understand, relate this. Now let's come back to this. So fine powders, when the particles are too small, they are tiny, they tend to react faster. You get? As a result, they make the reaction rate to be what? Fast. But when you have something like the particles are too big, the reaction will be what? Will be slow. So fine powders react faster than a what? A pellet. Is it clear on this part, or you're having some questions? It's clear? Hello? What about others? So we now know the effect of physical state on physical state of the reactants. Should I proceed to another factor that affects reaction rate? Okay, so physical state. Okay. So which ones are more faster between the homogeneous and the heterogeneous reactions, if I might ask, since you guys are saying you are clear? Homogeneous. Okay. So homogeneous are faster. Yes, thank you so much. So let's quickly look at the other factor that affects the reaction rate. Don't forget, whatever is here, we're trying to relate with what? The reaction rate, of which we know that that's how fast a chemical reaction occurs. So now, let's look at the reactant concentrations. Reactant concentration. So this one also has an effect on the reaction rate. It can either make the reaction rate faster or slow. You get? So now, reactants. Now, what do you have to know about reactants? So increasing reactant concentration. When you increase reactants, you increase the reactants. You get? Increasing reactant concentration generally increases reaction rate. You get? So the moment you increase the reactants, you expect the reaction rate to also to what? To be faster or to increase. You get? So now what about the opposite? If you decrease the reactants, what's the effect on the reaction rate? Do you expect it to increase or to be faster? No. Then the other thing that you need to know is the more you increase the concentration of the reactants, that will result into more molecules. You have more molecules. As a result, more molecules will be colliding. There will be more collisions. Do you know what makes a chemical reaction to occur? It's because of these collisions. If there are no collisions, then a reaction cannot occur. A reaction is occurring because of the collisions between the molecules. If the molecules are colliding, a reaction is taking place. You get? So the more you increase the concentration of the reactant, you expect the reaction rate to be faster or to increase because you are increasing the number of molecules. The more concentration, the more the reactant concentration, the more molecules. As a result, the more collisions between the reactants. As a result, what will be the effect on the reaction rate? It will what? It will be faster or it will be increase. Is it clear on the reactant concentrations? Yes. So what happens when you increase the reactant concentration? What will happen to the reaction rate? What will be the effect on the reaction rate? It will increase. Why is it increasing? It's because of you are increasing the number of concentration of reactants, which means there will be more molecules that will be colliding to each other. As a result, a chemical reaction will be what? Will be faster, therefore increasing the reaction rate. Thank you so much. Now let's look at the other factor that affects reaction rate, which is reaction temperature. Reaction temperature. I'm sure you're able to remember your chemistry well at your grade 12. What's the effect of temperature on the reaction rate? So now, here, reaction rate generally increases with increased temperature. So the moment you increase temperature, you're also increasing or making the reaction rate to be faster. It will increase. Apart from that, higher temperature, which is here, it will result into higher kinetic energy, which will result into more collisions between the molecules. As a result, they will be more energetic. The collisions will be more energetic. Once the collisions, once the molecules are colliding with each other, then the reaction it will be what? Faster. You get? So the higher the collisions, the faster the reaction rate. Is it clear on the effect of temperature? So higher temperature, more collisions. Higher temperature, more collisions, kinetic energy. You get? As a result, molecules move what? Faster, making the reaction rate to be faster. Okay, let's go to the other one. Yes, what's a catalyst? So, presence of a catalyst also has an effect on the reaction rate. What's a catalyst before I can continue, if you guys can remember? Hello? What's a catalyst? Wow. So it's therefore to speed a chemical reaction without itself changing. This is what they're trying to say here. So a catalyst is there, it has an effect on the reaction rate. It increases the reaction rate. And then the catalysts are not consumed in a chemical reaction. Yes, it's added to a chemical reaction, but it's not consumed. Its aim is to increase or to speed up the chemical reaction. You get? So catalysts, they modify the reaction pathway in a way that lowers the energy barrier. So these are the four factors that I've talked about, and I want you to know that because it's part of your syllabus that you're supposed to know. Should I proceed to the other part? Are you guys clear on the four factors that affect reaction rate? And there are some other factors, but I just wanted to focus on these important ones. Should I proceed on the other part? Are you guys clear? Guys, let's interact. Am I too fast? Am I slowing down or I'm still fast? Let's communicate. Are you guys too part of class? Are you guys following? Each one of you, like, are you following? Thank you so much. So now, let's look. So if you're following, um, do you remember the late? What did I say about the late before we look at the reaction rate? What can you remember about the late if you're able to follow? Wow, thank you. We're able to remember. What about the units? Can you remember the units? Okay, yeah, that's the simplest one. You can, yeah, yeah, m, which is capital time, modality per second, mole per second. Very good. Thank you. So now let's look at the reaction rate. Now let's look at the reaction rate. Rate, we talked about how speed a chemical reaction occurs. So now let's look at the reaction rate. What do you have to know about the reaction rate? Note that reaction rate, it tells how fast reactants are consumed or products are formed during a reaction. I repeat, reaction rate, it tells how fast reactants are consumed or products are formed during a reaction. Note that when you're reacting something, there's always something which is consumed, which are the, the reactants. You get? And there's something which is formed, which is the what? The product. So now we have the reaction rate, which tells how fast reactants are consumed or products are formed during a chemical reaction. So during a chemical reaction, how fast reactants are consumed, how fast products are formed. You get? That's the reason why we are studying chemical kinetics. We're trying to determine or to know how fast reactants are consumed or how fast products are formed during a reaction. So now, example, to make you understand. As I said, for chemists to study this, they initiate a chemical reaction. You get? And they observe time, if you remember. They observe what? Time. Because for you to determine how fast, you need time. And you need the concentrations of your reactants. You get? So as you can see this diagram here, let's focus on this first part. As you can see, at time zero, like T0, which is the initial, what's happening here? We are having lead molecules inside here. And then the concentration is 1.00 mole. That's the concentration we're having. We don't have anything here, but we expect that something will happen because this is a reaction. This is a reaction which is taking place here. Now, after some time, after 20 seconds, what can you notice here? You can see that there is something which is appearing in here. You get? Something is appearing. We can see blue molecules appearing. After 20 seconds, blue molecules have appeared. But even as these blue molecules have appeared, they are not more compared to the lead. As you can see, the concentration we're having 0.54 more, and then the other one we're having 0.46 more. So we still have more lead molecules compared to blue. You get here. Now, after another 20 seconds, as you can see, we're having 40. What's happening? We can see that there is an increase in the blue molecules compared to lead. Even the concentration can tell. The concentration for A has reduced to 0.30, and then the other one for B has what? Increased for these products. Have you seen? So which means as you keep on, as time keeps on going this side, we expect the blue molecules to be more than the lead. It can also reach to an extent whereby all lead molecules can all disappear and we can just remain with the blue molecules as time keeps on going. Now, what does this mean? It means that the reactants are what? Decreasing. Yes, the reactant is what? Decreasing, because lead is decreasing. Have you seen? This reactant which is there is decreasing as time progresses. So as time progresses, the reactants are what? Decreasing. Then as time progresses, what's happening now to the products? The product is what? Rising or increasing with time. The products are what? Increasing with time. They are appearing here. Is it clear before I make you understand more on this part? I repeat on this same part. Thank you so much. So now, like I said, let's focus on this first part. What can you see here? This is just a chemical reaction which chemists tried to initiate so that they can study the reaction rate. You get? So now, as you focus here, what are we having? We are having lead molecules, and they are just lead molecules throughout. And as you can see here, the concentration of lead is 1.00 mole. This is just the reactant part. And then for B, we don't know it, but we know that this is a reaction. For a reaction to be there, for it to be having the reactants, you expect to have the products later on. So for the products, it's like it's at initial, it's zero. We don't have anything here. You get? We don't have anything here, down here. We don't have anything. Now, as time progresses, as this reaction starts, after 20 seconds, the chemists realized or noticed that there is a change in the molecules. They noticed that blue molecules had to appear. You get? So blue molecules appeared after 20 seconds. And then what's happening to lead? So lead has started what? Decreasing. If you can compare the amount of the number, or just in terms of the number of these lead molecules, can you compare after 20 seconds? No. So what you can see is there's a decrease in the number of molecules for lead. And then there is a rise. There is something which is appearing. So here there is something, lead is disappearing while blue is appearing. Lead is disappearing, blue is appearing. And then if you check now the concentration, what's happening in terms of the concentration? Now lead has decreased. Have you seen from 1 now to 0.54? There is a decrease in terms of lead. You get? There is a decrease in terms of lead, which means lead is what? Disappearing. Lead molecules are disappearing. Now, what's happening to blue, which is just 0? It has started what? From 0 now, it's increasing. Blue is what? Increasing as time progresses. Lead is decreasing as time progresses. Now, after another 20 seconds, what can you notice here? We can see that we have more blue molecules compared to lead. So as you can see here, it keeps on decreasing from 0.54 to 0.30. Now what's happening to blue? Blue has what? Increased. So we can conclude that as time progresses, blue is rising or is appearing with time, is rising with time, while lead is decreasing with time. Are you now clear on this part before I make you understand what I mean? Hey guys, let's communicate. Are you clear on this part or you're not clear on my explanation? Yeah, clear. So what's happening between the blue and lead molecules? Which one is decreasing and which one is increasing? Very good. Thank you. So let's do this to make you understand. I'll do this. So let me do this. A, this A you're seeing is representing the reactant. Then this B you're seeing here is representing the what? The product. A for reactant, B for product. Now, A is decreasing. I will represent it with what? With a negative. B is increasing with a what? A positive. You get? Now here, we can come up with the let. If you remember, let is what? You remember let. Let of A. Let's come up with let of A, which is appearing. Let of A. Length of what? A is equal to what? So it can be changed. So since this is A, it's decreasing. I'll write, we know that this means what? Concentration also. So I'll write it like this. Negative. Why am I? Because I'm trying to come up with a length for this. For reactant A. It's decreasing, so I'll write a negative in front. So this is rate of what? Disappearance. Rate of disappearance, which is disappearing, negative. Now, I'll put the change in what? Concentration of A. You get? Over change in time. Why have I done this? Because we said rate is a change in concentration over time. Now, for this, just to find the rate of disappearance of A, which is decreasing, I've added a negative in front, showing that this is what? Decreasing with time. Now, let me do the same for B so that you see the difference. So for B, rate, we know that rate is equal to what? Concentration over time. So now, this one is increasing with time. So therefore, it's a positive. So here it will be just change in the concentration of what? The B molecules over change in time. Have you seen the difference? Can you ask me where the negative is coming from and the positive is coming from? Are you guys clear on how I've come up with this? Hello, you can ask. You can ask where you're not clear. Hello? Are you still guys part of class? Yes. So we're saying this delta you're seeing, this means change in concentration of A. This also delta means change in concentration what? Over time. As we remember, we said rate is concentration over time. So we're trying now to determine the rate of the reactant as well as the rate of the what? The product. Now we know that the reactant is decreasing with time. Therefore, there must be a negative in front. That's a negative they're seeing. Now, for the product is what? Appearing. So that's a rate of appearing. Will be represented what? With a positive in front, because this one is increasing with time. This one is decreasing with time. Is it clear? Are you all guys clear? Or if you're in need of any question, ask me before we proceed, because we need this for the other part. Any question on this part, or it's not clear? Tell me, I will repeat. Hello? Yeah, clear. Why is that, why are we having a negative in front for the reactant A? Okay. Mm. Oh, yeah, yeah. Thank you so much. So let me even just write it like this also. Let, thank you. You have gotten the point. Thank you. So let, this negative is for, I just didn't write nicely like that because of time. It's also affecting the time down. It's not just for the delta. So like that. So delta means just change. And then here it's just the concentration. Then this one is a what? A positive, because it's increasing with time. This is decreasing. The reactant is decreasing. As you can see, the number of molecules, as you keep going, as time progresses, the lead molecules are decreasing, and then the other one is increasing. You get? So decreasing from up going down. So that's a negative, not so. Then increasing starting from down going up, and that's a what? A positive. So A is represented by this one. A is for this one, which is decreasing, which is having a what? A negative. Was it decreasing? Then B will have a positive because it's rising. The blue molecules are appearing. Others, what about others? Are others clear? Let me know before I go to the other part. Because if you can't understand this part, it will affect the other part. Hello? Hello? Others, can you say something? Are you guys clear? Let me know. Fast, before we clear. Okay, so the same one who has said clear. Why is B positive? Like, why is it B positive? Like, why are we having this side a positive and this side a negative? Just try to make me understand. I just want to see if you guys are in class. Class is more interesting if you guys are interacting. We are interacting. Then I'm just talking to myself. Okay, I assume you guys are clear without wasting much of your time. Now, kinetics of reaction can be represented on a graph. So as you can see, now this time reactant will be represented by R, product will be represented by what? P. So the same thing which is happening here. As you have noticed, for A, here I will represent R for A, like the way we did, and then this one will represent B, if you remember what was happening that side. So if you remember, for A, the reactant was what was happening for A? A was what? Disappearing. Disappearance of reactant, which was decaying, decreasing. And then B, there was an appearance of what? Blue molecules. That was what? Appearance of a product, which means same as what? Lyse. So whatever was happening there was a decay and there was a what? A lyse. A decay of a reactant. Reactant was decreasing with time. A product was what? Increasing or rising with time. Now let's look at this graph now. So as you can see, this side, that's molar concentration plotted against what? Time. Now, as you can see, here, that's where the initial concentration is at T0. Yes, your zero time is here, but for the initial concentration, it's starting here. And it's decreasing with time. You get? So as the reaction starts, the reactant will be decreasing with time. And it keeps on going to the positive infinity. It keeps on going like that. Now, where will be the final? Because that's the initial now. That's where it's starting from. Where will be the final? So the final concentration at T infinity, it keeps on going. So that's why they just had to take it back to find the final. You get? Yes. Now, let's look at this other one. The product, which was what? Rising or increasing with time. What was happening here? Where is it supposed to start from? This one starts now from the initial time 0 also. You get? From here now. So as you can see, this one is rising, increasing with time. So as the reactant was decreasing with time, the product was increasing with time. And it kept on going to the positive infinity this side. So since it keeps on going, the final concentration will just be obtained like the final concentration at T infinity, or at initial at this concentration this side. Is it clear? Have I made you understand this graph, or are you still having questions? Let me know. Clear? You have noticed what's happening in terms of the curves. So what's appearing, what's increasing, what's decreasing between the reactants and the products? What's increasing, what's decreasing? Exactly. Yes. The products. Yes. So that's what happens in a chemical reaction. So reactants will start decreasing and then the product will start forming, rising. Have you seen what happens there? Thank you. I have this another one to make you understand. If you didn't understand that side, we have this now. So R representing the reactant and this reaction is either way possible. The forward and the reverse is equal. A reactant can be converted to form a product, and the product can be broken down to form the what? The reactant. So either way possible, it's possible. Now, let's look at this. Now they have combined the reactant and the product on one graph now. So as you can see, what's starting on initial 0? It's the product, which is starting from initial time here. So it's increasing with time. So as you can see, it's going to the positive infinity, to the positive numbers this side. So appearance of a product, and this one is very fast. You get? Now we have another one which is coming, which is faint. Now when it's passing like it's a faint, which means it's a slow reaction. Now let's look at this now, the blue one, which is the reactant. What's happening? As time progresses, the reactant is decreasing with time. You get? So here, that's the initial, that's where it is. And then the final keeps on going there and see, at equilibrium. So this one represents now fast reaction for the decreasing, the blue one. And then the faint one means disappearance of the reactant is what? Slow. Is it clear on this part before I can go to the other part? Hello? Okay, so yeah, let's just do the other parts. So now types of LEDs. Let's look at types of LED. One, we have the average LED. The second one, we have the instantaneous LED. The third one, we have the initial LED. So now let's look at the average LED. So for the sake of time, I'll end at the average LED because I just wanted to introduce, but I have more. Unless if you tell me I'm tired, I can keep going because I have energy for you guys. I want you to understand this. So now, average LED. What do you understand by average LED? What average LED? Average LED. What do you understand by that? Note that average LED of a reaction measures how fast the concentration of a reactant decreases or product increases over a specified time interval. I repeat, average rate of a reaction measures how fast the concentration of a reactant decreases. Have you seen how fast the concentration of the reactant are decreasing with time, or a product increases over a specified time interval? So average now just measures the time for the whole journey of a chemical reaction, whole journey, you get, and the time will be specified. So now let me try to make you understand here what I mean. So average rate, I'll write A, the formula, to represent average, and then R to represent what? The rate. The rate is equal to, if you remember, average rate also is equal to what? Change in concentration. You get? Change in what? Concentration. Concentration of either the what? The product or the reactant. I don't know why my thing is very slow, the thing I'm using, but I'll try by all means to do. Over what? Change in what? Time. Yes, over change in what? Time. So average rate is equal to what? Change in concentration of either the reactant or the product over change in what? Time. So now from here, what if we're dealing with the reactant A? You remember what happened there? Let me just do this. We are focusing on the A part, the reactant, which is decreasing. We focus much on this one, which is decreasing. So average rate. Let's come up with the average rate. And then our concentration, we'll relate it with what? We'll replace our concentration with this A, which is the concentration for the reactant. Changing the concentration of the what? Reactant, like that. Over change in time. Now, do you know that this one is decreasing, not so? Hello? On this part, before I proceed, are you guys clear? A is decreasing, not so? So we expect where a negative average rate is equal to what? Negative change of A, you get, over change in time. So this is the formula. So, and let me write it nicely, because you need this. Yes, let me just love this part. The negative is affecting, is for everything, not, yeah, it's like this. This negative should be independent on its own, like that. So this is the formula now for average rate. So average rate is equal to minus, because of its decreasing, it's disappearing with time. Change in concentration of A over change in what? Time. But there are times where you are having this concentration. We can have the initial concentration as well as the final concentration. We can have the initial concentration as well as the final concentration. So we're going to say minus this. And then let me just do this. Open bracket. We'll say, for example, we're having the final concentration minus initial 1. This will present by 1, meaning initial concentration, over time also, where it's starting from, we can have T2, the final time, minus the initial time. Have you seen? Because the concentration, you are having it at the start of the reaction, which is the initial, also to the final. It must be measured. Is it clear on this part? Thank you so much. So now, let's look at this now. So try to take a screenshot here. Take a screenshot on this formula so that I can lab this. Have you managed to take a screenshot? Hello? Have you mastered the formula? If I ask you, you write this? Okay. So now, have you seen now? That thing we are able to see it's this now. So change in time, you can have at T1, the initial time, you get? And then from there, on this curve, you obtain to this y-axis, which is representing the what? The concentration. And then here at T2, that's your final time. You can come to your curve and come back to the y-axis to obtain your final concentration. And then the rate measured will depend on how long change in time is. Have you seen? The rate measured will depend on how long change in time is, the average rate. So now let's just quickly, the units, you remember these units? Yes, now let's just solve one question, then we can call it a night. And then I'll give you one task, which you're supposed to answer. Though I wasn't supposed to end here, but I want you first to go through this, you assimilate the information, then we'll continue. So now, what's the question? Calculate the average rate at which A, which is the concentration A, disappears. Have you seen? A disappears over the time interval. They have 20 seconds to 40 seconds. How can we answer this one? We are focusing on 20 seconds to 40. That's a time interval. So between this, we need to obtain something. Now, let's come up with a formula and the data. First, let's come up with our data. First, before that, what's the formula? If you remember, what's the formula for average rate? What's the formula? Very good. So average rate, let me write like this. Average rate is equal to, repeat what you said. Very good. Now you're forgetting something. What's about the negative in front? Because it's disappearing. Have you seen? They're focusing on that one which is disappearing. For something to disappear, for this to disappear, the concentration to disappear, which means it's what? Decreasing. So there is that negative, and in front. Not only that, this reactant, yes, concentration, they have mentioned now A. So our concentration on top, we write it as what? Change in what? Concentration of this A they have mentioned over as you said, change in what? Time. Like that. Now, here you know that they have given us the interval 20 and 40. Now, between 20 and 40, we have our final and our initial. So our initial, we'll get our initial from here, our final from here. You get? Now, our aim, we're focusing on just A, not B. They have mentioned A, the reactant, not the product. You get? So our aim is to focus on A. You get? So now, let's come up first with our, so because of that, we know that we're having two things. So we can write it like this now. So the formula, we extend it like this. It will be a wrong one, or let me just write it down here. So it will be average rate is equal to negative change of what? So let me subtract the what? The change, so that I just replace it with what should be so here. So we said it can also be what? Open bracket, final concentration, not so, 2 minus initial. You remember? Over T2, the final, minus T initial. Then we can replace. Now, before we replace, let's collect the data for time. T1. What do you think will be our T1? Our T1 will be collected here on 20. So that's 20, not so. Our T2 will be what? 40. That's the final, not so. Now, what will be our A1 initial, and then our A2, the concentration 2? Let's start with our A1, which is the initial. Is this one here, not so? Because this is the initial, yes, the initial from here now to here. So that's what? 0. Hello? What will be our initial? 0.54. Why is it our initial phase? The one which is ending is the final. Very good. Because it's just the beginning. Okay, very good. So that's it. 0, 4, yes, more. Now, this one for the final to be what? 0.3 more. Okay, then we can replace. So we're going to have something like what? Negative should always be in front, like that. Then what's our A2? That's 0.30 more. Minus, even forget about that, but for the sake of space, let's not add the moles, because there is no enough space. We'll add that later. The units later. Okay, so we're even done. I just want to, yes, minus 0.54. Yes, and then the units you can write it outside if you want, like that. More. Or just the capital letter M. The M, the big M. Yes. Then over, what's our time? That's T2, that's 40, minus 20. Guys, let's subtract. What is 0.30 minus 0.54? What are you getting? 0.30 minus 0.54. I'm getting something like, what are you getting? Negative 0.24. Very good. And then the M is on top like that, capital M, presenting the molarity. And then over, that's 20, not so? Yes. What are you getting after dividing with 20? What are you getting after? So sorry, I've forgotten something here. Like there's a negative on its own. This one should have the negative on its own also. Yes, because that one, yes. Yes, we're done. We're just trying to conclude this. Okay, so as you know, the average rate, the thing is so slow. So this is having its own negative, and that is having its own what? Negative. Don't forget. Then it's still coming down like that. So now when you divide, what are you getting here? Negative what? 0.012. And then, do you know, this negative will kill with that negative. Therefore, your average rate, the final answer, will be what? A positive. It's always a positive quantity. You get? It's always a positive. So it's going to be 0.012. You can just use these units if you want. The capital letter M per seconds. Or if you want to add the other one, then you are done. Guys, was this clear? Have you managed to know how to find the average rate? Huh? It was clear, like clear. You can't fail a question if you're asked about the average rate. Okay, so let's do this. This is your task now. Take a screenshot, then you'll be able to send via my WhatsApp number down here. Then from there, we'll proceed to instantaneous. This is the next part that I want you to understand. Now, for the sake of time, you need to list. Yes, so have you managed to take a screenshot? What time do I expect my answers? Huh? Tomorrow afternoon. You want to Facebook some or you WhatsApp some. Okay, so how was class? I want to hear your views. Is this clear? Can you see yourself changing or you're just the same? You see yourself changing. What about others? I want to know so that I can polish up. If you are not clear, you should tell me if I'm too fast. Next time, sir, try to be this. Is there any addition, anything else that you feel like I need to work on? Is it my voice projection? How is it? The lesson is clear. So you guys, you see yourself changing with me, not so? Yes, so I'll try by all means to give you the foundation whereby when you go that side, I'm telling you, you'll be seeing everything simple because of the concepts I'm giving you. I never wanted to start answering questions, past paper questions or tutorial sheet questions because once you're just mastering those solutions without the concept, believe me, that's nothing. So watch this video, understand the rate of disappearance, what was happening there, and the appearance. Those, whatever I was explaining, that's a good foundation that you need under this topic. Thank you so much. In your inbox, I'll get back to you. I'll ask you questions in your inbox. You tell me about the appearance and disappearance. Where was the negative coming from? Where was this coming from? I want you guys to begin with the concept because once you remember the concept, it's very it's very simple. You can't forget things. You get? Thank you so much, and I'll upload this video and I'll send into the group. Thank you so much. For any question, anything else, feel free to inbox me. And don't forget to subscribe to my YouTube channel as well as my Facebook page. Thank you so much. Any addition? Any subtraction before I end? Any addition? Any subtraction? Mr. Kreman, is there anything? Mr. Sorry, Chimwemo Chambish, are you clear? Dines. Okay, Dines. Okay, she's clear. What about Janet? What about Janet? You're clear? Okay, I'm dancing here. You guys are clear. You know, it feels nice. It feels nice because it's like I didn't waste my time. Teaching without you understand. That's why, guys, next time, try by all means to be communicating. Let's interact. Let me know. Sorry, first, repeat. Let's just interact. I just like it like that. Thank you so much. Let me start dancing since you guys are clear. The foundation is strong. You understand this. And if you're just serious, we'll finish the tutorial sheets. We'll finish everything. Thank you so much. Have a good night. Any queries, any questions? You have my WhatsApp number.